Welcome to the video on image restoration and estimation of degradation model. This topic is crucial in digital image processing as it helps improve image quality by reversing degradation effects. Image restoration is to restore a degraded image back to the original image. Image enhancement is to manipulate the image so that it is suitable for a specific application. As in image enhancement, the principal goal of restoration techniques is to improve an image in some predefined sense. Although there are areas of overlap, image enhancement is largely a subjective process, while image restoration is for the most part an objective process. Restoration attempts to recover an image that has been degraded by using a priori knowledge of the degradation phenomenon. Thus, restoration techniques are oriented toward modeling the degradation and applying the inverse process in order to recover the original image. Let's see the mathematical representation of degradation model. We model image degradation as an operator, capital H, that, together with an additive noise term, operates on an input image f of x, y to produce a degraded image g of x, y. Given g of x, y, some knowledge about h and some knowledge about the additive noise, term h of x, I, the objective of restoration is to obtain an estimate f cap of x, I of the original image. We want the estimate to be as close as possible to the original image, and in general, the more we know about capital H and small h, the closer f cap of x, y will be to f of x, y. If capital H is a linear position invariant operator, then the degraded image is given in the spatial domain equation, where h of x, e is the spatial representation of the degradation function, and the symbol asterisk indicates convolution. From the convolution theorem, the equivalent of this equation in the frequency domain equation, where the terms in capital letters are the Fourier transforms of the corresponding time function. These two equations are the foundation for most of the restoration processes. Noise in images can arise from various sources, affecting the overall image quality. One major source is acquisition noise, which occurs due to low light levels or sensor temperature variations during image capture. Another common source is transmission noise, which results from factors like lightning, atmospheric disturbances, or interference in communication channels during image transmission. There are different types of noise that affect images. White noise has a constant Fourier spectrum, meaning its effect is uniform across the image. Gaussian noise is the most common type found in natural images, often caused by thermal fluctuations in electronic sensors. Salt and pepper noise appears as random white and black pixels, usually caused by sudden transmission disturbances or faulty sensors. Understanding the type and source of noise is essential for selecting the right restoration technique. Estimation of degradation model. There are three principal ways to estimate the degradation function for use in image restoration. So, 1. Observation. 2. Experimentation. 3. Mathematical modeling. The major purpose is to estimate h of x, y or h of u, v. The reason is, if we know exactly h of x, y, regardless of noise, we can do deconvolution to get f of x, y back from g of x, y. Let's see these methods in detail. Estimating the degradation function from the image. Suppose we are given a degraded image without any knowledge about the degradation function, capital H. Based on the assumption that the image was degraded by a linear position invariant process, one way to estimate capital H is to gather information from the image itself. For example, if the image is blurred, we can look at a small rectangular section of the image containing sample structures, like part of an object and the background. In order to reduce the effect of noise, we would look for an area in which the signal content is strong. for example, an area of high contrast. The next step would be to process the subimage to arrive at a result that is as unblurred as possible. Let the observed subimage be denoted by gs of x comma y, and let the processed subimage be denoted by fs of x comma y. Then, assuming that the effect of noise is negligible because of our choice of a strong signal area, it follows from the equation. From the characteristics of this function, we then deduce the complete degradation function h of u comma v based on our assumption of position invariance. Clearly, this is a laborious process used only in very specific circumstances, such as restoring an old photograph of historical value. Next is estimation by experimentation. If equipment similar to the equipment used to acquire the degraded image is available, it is possible in principle to obtain an accurate estimate of the degradation. Images similar to the degraded image can be acquired with various system settings until they are degraded as closely as possible to the image we wish to restore. Then the idea is to obtain the impulse response of the degradation by imagining an impulse, small dot of light, using the same system settings. An impulse is simulated by a bright dot of light, as bright as possible to reduce the effect of noise to negligible values. Then, recalling that the Fourier transform of an impulse is a constant, then the degradation function is as shown here, whereas before g of u comma v is the Fourier transform of the observed image, and capital A is a constant describing the strength of the impulse. Next is estimation by modeling. Degradation modeling has been used for many years because of the insight it provides into the image restoration problem. In some cases, the model can even take into account environmental conditions that cause degradations. For example, let's see the atmospheric turbulence model. A well-known degradation model proposed by Hufnagel and Stanley, 1964, is based on the physical characteristics of atmospheric turbulence. This model follows the equation shown here, where k is a constant that depends on the nature of the turbulence. With the exception of the 5 by 6 power in the exponent, this equation has a form similar to the Gaussian low-pass filter, LPF, transfer function. In fact, the Gaussian LPF is sometimes used to model mild, uniform blurring. Simulated blur examples. Figures show examples obtained by simulating blurring an image using this equation with different values of k. Here, k equals 0.025 is representing severe turbulence, k is 0.01 is representing mild turbulence, k equals 0.025 is representing low turbulence. These values demonstrate how different levels of atmospheric turbulence impact image clarity and how restoration techniques can be applied accordingly. Here's how the different estimation methods are used in specific applications. Forensics for improving surveillance footage. Here, estimating the degradation function from the image is used. The reason is, if the degradation pattern is unknown but present in the image, forensic experts can extract it from a portion of the image with strong signal content. Next application is medical imaging. For example, enhancing MRI, CT, and X-ray images. Here, estimation by experimentation is used. The reason is, when medical imaging equipment is available, experiments can be conducted by capturing images with controlled settings to replicate degradation effects. Next application is satellite image processing and astronomy. Here, estimation by modeling is used. The reason is, atmospheric turbulence and other environmental factors are best modeled using known degradation equations, such as those developed for atmospheric blur in satellite imaging. Thank you.